والتفوق بإذن الله.
My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the AC circuits. AC circuits are the circuits that are powered by an AC dynamo. They may include inductors, coils, capacitors, and resistors. And also we'll learn about a state known as resonance state. So let's get started. AC circuits. Okay, first of all, AC current in a non-inductive ohmic resistance, denoted by R. What is meant by non-inductive ohmic resistance? Okay, it is a coil which is doubly wound, so no EMF can be induced by self-induction. When the circuit shown in front of you is closed, the instantaneous potential difference across the resistor is given by, yes, the voltage of the dynamo. V instantaneous voltage is equal to V maximum sine omega t. This is the first equation. We want the relation that represents the current. So this equation is divided by the resistance. And let me remind you something, omega t is the phase angle. Dividing both sides of equation 1 by R, we'll obtain the following equation. So instantaneous voltage over resistance equals V maximum, okay, over R sine omega t. V over R will give the instantaneous current. Okay, so we can say instantaneous current is equal to, yes, I maximum sine omega t. If we compare the second equation to the first, okay, the voltage and the current will have the same phase angle. So the current and the voltage are drawn to coincide on each other. Okay, they have the same phase angle. Okay, so from equation 1 and 2, the voltage and current are in phase. And what about an AC in a pure inductor, in a pure inductance? What is a pure inductor? It is an inductive coil of 0 ohmic resistance. The resistance of the coil is considered to be equal 0. We call it pure inductor, pure inductance, and it is denoted by capital L. Okay, if we apply Ohm's law to a closed circuit, the current through the circuit is given from, yes, the following relation. I is equal to V minus L di over dt over R. So we can say the product of IR is equal to V minus L d by dt to the current. IR is equal to 0 because R is, yes, 0. So we can say V is equal to L di over dt. Okay, so if we want to obtain the instantaneous voltage, okay, it is equal to L, and we need to obtain the first derivative of the current. Current is given by the relation I is equal to I maximum sine omega t. So V is equal to L, okay, first derivative of the current. Current is equal to I maximum sine omega t. So we can say V is equal to L I maximum omega cosine omega t. And we will convert cosine into sine by adding pi over 2. So your attention please. The last equation can be written as follows. V Li maximum omega sine omega t plus pi over 2. Okay. Why we did this particular thing? To compare the two phase angles. The current, phase angle of the current is omega t, phase angle of the voltage omega t plus pi over 2. Okay, so we can say V is equal to V maximum sine between two brackets omega t plus pi over 2. But the current, instantaneous current, is equal to I maximum sine omega t. So if we compare the phase angles, we can say, yes, we can say that the current in a pure inductance lags pi over 2 behind the voltage. Okay, that's to say the voltage leads on the current by 90, pi over 2. It is shown in front of you on the screen. Okay, the voltage leads on the current. It means the current passes its maxima a quarter cycle later than the voltage. Okay, we've got important hints here. Since V maximum is equal to Li maximum omega, so we can say V maximum over I maximum is equal to L omega, and it is, yes, it gives the opposition. So V maximum over I maximum, which is equal to L omega, is an inductive reactance, and it is denoted by XL. So XL is equal to 2 pi FL. F is the frequency. And what about the unit? Any opposition, any resistance is measured in ohm, and frequency is measured in hertz, and L inductance in Henry. So ohm is equal to hertz times Henry. And we can define inductive reactance. It is defined as the opposition that a pure inductance offers to the passage of the alternating current due to, yes, its self-inductance. So once again, inductive reactance is defined as the opposition that a pure inductance offers to the passage of the alternating current due to, yes, self-inductance. From the equation XL is equal to 2 pi FL, the factors that affect the inductive reactance are, of course, first of all, the frequency. XL is directly proportional to the frequency. Second factor is the inductance of the coil. XL is proportional to, yes, the inductance. Okay, and now we've got very important piece of information. If we have many coils connected in series, when inductors are connected in series, yes, XL total is equal to XL1 plus XL2 plus XL3 and so on. And of course it will be equal to N XL1 if they've got the same value. And what if they are connected in parallel? 1 over XL, okay, 1 over the total reactance equals 1 over XL1 plus 1 over XL2 plus 1 over XL3. And of course, XL total equals XL over N when the inductors have the same value. Okay, since XL is equal to V max over I maximum, so divided both sides by 0.707, we can say XL is equal to V effective over current effective. And now AC current and voltage in a capacitor. Okay, in front of you we've got, yes, a circuit that contains an AC supply and a capacitor. Reactance of the capacitor is denoted by XC. We call it capacitive reactance or capacitive reactance. The charge on the plate of the capacitor is determined from the relation Q, the charge, equals C, the capacity, and the voltage. Okay, so Q equals CV, where C is the capacitance of the capacitor. And what about the voltage? Instantaneous voltage is determined from the equation V equals V maximum sine omega t. And what about the current? It is obtained from the relation. It is the first derivative of the charge with time. So I equals D, Q equals, yes, C V maximum sine omega t. Okay, so we can say I is equal to C omega V maximum cosine omega t. And once again, cosine is converted into sine, and we have to add pi over 2. So I instantaneous is equal to C omega V maximum sine omega t plus pi over 2. So we can say the instantaneous current is equal to the maximum current sine between two brackets omega t plus pi over 2, where I maximum, of course, is equal to C omega V max. From equation 1 and 2, it is clear that the current leads the voltage by pi over 2. Let me say it again. From the two equations, equation 1 and 2, it is clear that the current leads the voltage by pi over 2. From the relation I maximum is equal to C, yes, omega V, we can obtain the, yes, reactance, capacitive reactance or capacitive reactance. It's all easy. All you have to do is to get V maximum over I maximum, which is equal to V effective over I effective. Okay, we can obtain the capacitive reactance. We can obtain the capacitive reactance as follows. I maximum is equal to C omega V maximum. So XC, capacitive reactance, is equal to V maximum over I maximum. It is 1 over C omega. And omega is equal to, yes, 2 pi f. So XC equals 1 over 2 pi f C. This is the relation that determines the capacitive, yes, reactance. And now connection of capacitors when they are connected in series and connected in parallel. We'll learn about this. So connection of capacitors. First of all, what about the series connection? Since the total voltage equals V1 plus V2 plus V3, we can say V equals Q over C. So total charge over total capacitance equal Q over C1 plus Q over C2 plus Q over C3. So we can say 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3 when they are connected in series. And C total is equal to C over N if they've got the same value. And what if they are connected in parallel? Q is equal to Q1 plus Q2 plus Q3. So VC is equal to VC1 plus VC2 plus VC3. So we can say total capacitance equals C1 plus C2 plus C3 when they are connected in parallel. So total capacitance is equal to NC if each one of them, or if they have the same value. Okay, when the capacitors have the same capacity. And now talking about another AC circuit, L and R. L is the inductance, pure inductance, R ohmic resistor in series in an AC circuit. The voltage across the resistor VR is in phase with the current, but VL leads by 90. The current, thus the two voltages, can be drawn to a scale shown in front of you. VR is in phase with the current drawn on the same line. They coincide, but the voltage leads by voltage across the inductor by 90. Okay. So the total voltage is obtained by, yes, using Pythagoras. It is square root VL squared plus VR squared. So it is equal to, of course, VL equals IXL. So VL is squared equals I squared XL squared plus I squared R squared. So we can say V is equal to I square root XL squared plus R squared. Okay, and it is all easy to obtain the impedance now. We've got voltage and current. So, yes, thank you very much. Voltage divided by the current will give the impedance denoted by Z. It is equal to XL square root XL squared plus R squared, where Z is the impedance of the circuit. Okay. From the figure, the voltage leads on the current by an angle theta, the previous figure. If we want to determine the value of the angle, tan theta equals VL over VR. So tan theta equals IXL over IR. The current will be crossed out. So tan theta equals XL over R. And this way, the value of theta equals tan, yes, to power negative 1 XL over R. We've got important hints. Impedance, definition of impedance, yes, is the quantity that determines the current flowing in a circuit that contains reactance and resistance. Let me say it again. What is meant by impedance? Impedance is the quantity that determines the current flowing in a circuit that contains reactance and resistance. It is the combined effect of reactance and the ohmic resistance on the passage of the alternating current. And now we've got another circuit, C and R in series in an AC circuit. Okay, VR is in phase with the current, but VC lags by 90 on the current. Thus the two voltages can be drawn to a scale, and V, the total voltage, is equal to square root VC squared plus VR squared. So V is equal to square root I squared XC squared plus I squared R squared. So we can say V is equal to I square root XC squared plus R squared. V over I will give the impedance So Z equals V over I, which is in this case square root XC squared plus R squared, where Z is the impedance of the circuit. From the figure, the voltage leads on the current by an angle theta. Okay, so tan theta is equal to Vc over Vr. It follows tan theta is equal to Vc. How to obtain Vc? It is the product of the current and the capacitive reactance, but Vr is equal to IR. The current will be crossed out, so tan theta equals XC over R. In this way, we can obtain the value of the angle theta. Okay. And now we've got a circuit that contains a pure inductor and a capacitor. Okay. So we've got a circuit that contains C and L in series in an AC circuit. The total voltage is determined from the relation VL minus VC. When VL is greater than VC, okay, or VC minus VL when VC is greater than VL. Total reactance, of course, is denoted by X is equal to XL minus XC when XL is greater than XC, and XC minus XL when XC is greater than XL. And now we've got a circuit that contains the whole components, the three components, the resistor, the capacitor, and the inductor. Okay, voltage across the resistor is denoted by VR, and it is IR. Voltage across the capacitor is VC, and it is the product of I, XC. Across the inductor, it is VL, and it is IXL. So we've got a circuit, we call it RLC series circuit. If VL is greater than VC, the total voltage is given from the equation square root VR squared plus between two brackets VL minus VC all squared. So we can say V is equal to square root I squared R squared plus I squared between two brackets XL minus XC all squared. So V is equal to I square root R squared plus XL minus XC squared. So the impedance, which is V over I and is denoted by Z, is equal to square root R squared plus XL minus XC all squared. Okay, this when XL is greater than XC. Okay, and in front of you is the vector diagrams. In this case, the total voltage leads on the current by an angle theta. The total voltage leads on the current by an angle theta. And if we want to determine the value of the angle theta, tan theta is equal to VL minus VC over VR. So tan theta equals IXL minus IXC over IR. VL is equal to IXL. VC is equal to IXC. And VR is the product of the current and the resistance. And of course, the current will be crossed out. So tan theta equals XL minus XC over R. And in this way, the value of the angle itself, theta, can be determined. Tan negative 1 XL minus XC over R. Second case, if the value of VC is greater than the value of VL. the total voltage is determined from the equation V is equal to square root VR squared plus VC minus VL, because VC is greater than VL, all squared. Okay, voltage is the product of current and resistance, or anything that represents resistance. So VR squared equals I squared R squared, okay, plus I squared XC minus XL squared. I squared, yes, will be drawn out in form of I, so we can say V is equal to I square root R squared plus between two brackets XC minus XL squared. So we can obtain the impedance denoted by Z. It is V over I, it is square root R squared plus XC minus XL all squared. Okay, in this case the total voltage lags on the current by an angle theta. Okay, the total voltage as shown in front of you lags by an angle theta, and we want to determine the value of the angle theta. So tan theta equals Vc minus Vl over Vr, and of course it is equal to Ixc minus Ixl over Ir, and the current will be crossed out. So tan theta equals Xc minus Xl over R, and in this way we've managed to obtain the value of the angle itself. And what about the third and it is very important state? We call it the resonance state. The third case here, we call it resonance state. Okay, how to obtain a state of resonance? Since the inductance causes the current to lag behind the voltage, and the capacitance causes the current to lead on the voltage, therefore they can be adjusted to cancel the effect of each other. At resonance, the current, what happens? At resonance, the current is at its peak value, its maximum value, and the impedance is at its minimum. Impedance is minimum, and it is just equal to the value of the ohmic resistance. So once again, at resonance, the current is at its peak value, and the impedance is at its minimum value. Impedance is equal to R. At resonance, VL is equal to VC because XL is equal to XC. Okay, and as I said, the total voltage will be the voltage across the ohmic resistor. So V is equal to VR. Dead is minimum, and it's just equal to R. And total voltage and current are in phase. Thus, when we reach a resonance state, VL equals VC, XL equals XC, total voltage equals the voltage across the resistor, Z is equal to R, V and I are in phase. So the phase angle between total voltage and current is 0. At resonance, as I said, XL is equal to XC, so 2 pi FL is equal to 1 over 2 pi FC. It follows 1 is equal to the product of 2 pi FL times 2 pi FC. So it is equal to 4 pi squared F squared LC. And the frequency squared will be 1 over 4 pi squared LC. So the frequency at which resonance occurs, we call it resonant frequency, and it is equal to square root 1 over 4 pi squared LC. So resonant frequency is equal to 1 over 2 pi square root, yes, L times C. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.